All right, let's go ahead and get started. Hello again, welcome, and thank you for joining our MEST webinar today. Today we have a very special topic and a very special guest speaker whom I'm very pleased to introduce next. Our speaker today is Professor Todd Austin, who is a professor of electrical engineering and computer science at the University of Michigan in Ann Arbor. His research interests include computer architecture, robust and secure system design, hardware and software verification, and performance analysis tools and techniques. From 2012 to 2017, he was a director of CFAR, the Center for Future Architecture Research, a multi-university SRC and DARPA funded center that was seeking technologies to scale the performance and efficiency of future computing systems. Prior to joining academia, he was a senior computer architect in Intel's Microcomputer Research Lab, a product-oriented research laboratory in Hillsboro, Oregon. Todd is the first to take credit, and of course, the last to accept blame for creating the Simple Scalar toolset, a popular collection of computer architecture performance analysis tools. He is co-author of the undergraduate computer architecture textbook, Structured Computer Architecture. In addition to his work in academia, Todd is also the founder of Simple Scalar LLC and co-founder of Agita Labs and InTempo Design. In 2002, he was a Sloan Research Fellow, and in 2007, he received the ACM Maurice Wilkes Award for innovative contributions in computer architecture, including the Simple Scalar Toolkit and the Diva and Razor architectures. Professor Austin is an IEEE Fellow and received his PhD in computer science from the University of Wisconsin in 1996. Without further ado, I would like to introduce and give you the floor, Professor Austin.
Thank you, Waleed. Thank you for the introduction, the very nice introduction, and thank you, MEST, for organizing this series. I've been attending it all throughout the pandemic. It's really been kind of my little technical space that I could go to and enjoy some really interesting hardware security work. So thank you so much for organizing this. It's really been valuable. Today, I'm going to talk about some of our work at University of Michigan that started about 5 years ago with a DARPA program called SITH, S-S-I-T-H, which was a hardware security program in DARPA. At the time, I was working on more vulnerability-centric techniques to build more secure systems. In fact, looking for ways to eliminate control flow attacks completely by using clever compiling techniques with some hardware support. And at the time this DARPA program got started, they wanted you to cover like 7 classes of vulnerabilities. And it had taken me 4 years to do one class, so I'd need like, you know, an additional 21 years or 25 years to get this all done. So we really kind of retooled our entire approach to system security in a way that we could really ignore vulnerabilities. And that's the thing you're going to see through this whole talk. We don't care about vulnerabilities because that's not what we're trying to protect. And because of that, you really create a more durable solution. And this led to a lot of activity with DARPA, and then finally, commercialization activity. I'm currently on leave from the University of Michigan at Agita Labs, focusing on getting this technology commercialized. So I'm going to talk a teeny bit about that. So let's just start here by looking at the state, the dour state of today's security defenses. I'm sure everybody knows this, but I think we need to take a little bit broader look at what we consider security. You know, of course, we want to worry about program security. Are people hacking into our programs and trying to steal our data? Yeah, all the time. And if you live in the United States, then you probably heard of the Equifax breach in 2017, where 50% of Americans had their financial credentials, your name, date of birth, social security number, address, stolen in that attack by a yet as to be discovered entity. You know, I mean, and this was just, you know, a system security attack, remote code injection. You know, we gotta get our hands around these data breaches, or it's just not gonna, you know, at some point we won't be able to scale the cloud anymore because it will just be too dangerous. Also, from a security standpoint, we can't trust our programmers and our programming methodology anymore, really. If you followed the SolarWinds hack, where somebody hacked into SolarWinds and then added malicious code to their system that then traveled out to all their customers and provided backdoors to all their customers. I mean, this is another issue that I think we need to be worried about. Also, backdoors in hardware, something I know the MEST Center's really focused on. So why can't we just fix this? Why can't we just make the investment and see once and for all that security is fixed and that we don't have to worry about it anymore? And there's really just two reasons for this, for system security. One reason is software, okay? And not just software that has bugs in it, software. The existence of software means a system, if it trusts the software in any way, cannot be secure. And people always love to argue with me on this. I love to engage people on this topic. We have things like formal verification to verify software, and that is useful. It can find a lot of vulnerabilities. But if you look at this graph, you're always up against programmers, and programmers just are too creative. This graph shows you the amount of code that is in a commercial airline over time when the wheels leave the ground running. How many lines of code? And today it's about 50 million lines of code inside these airlines, Boeing in blue, Airbus in red, when the wheels leave the ground. 50 million lines. If you study software engineering, about 1 out of every 20 lines is going to have a bug in it. If you study security verification, you're going to know a sizable fraction of those bugs are going to be exploitable. And so what do you have? You have a system that is completely exploitable. And if you can do formal analysis on it, maybe you can find some of those bugs. But then you know what you're going to do? You're going to put that software on my microarchitecture, and I'm going to create a whole mess of other microarchitecture vulnerabilities, and the software can't do anything about that. And that's really the other side of the coin, is side channels. How do you keep data secret? People are hacking into programs to steal data. They're using the vulnerabilities in software to get into the software. Even if you could stop that, you'd still have the problem that you could use all these side channels, the specters, the meltdowns, the zombie loads, etc. These are non-trivial to stop in hardware, and they're completely uncontrollable by software. So it's really a difficult challenge. And in my personal opinion, you can't use software to fix either of these problems. You can't use software to fix software, because you just add more software, you're making the problem worse. And you can't use software to fix side channels, because half of the side channels are in the part of the system that software has no control over, the microarchitecture, the power draw, etc. So this is why I love hardware security. And I would say to students on the line here, if you're studying hardware security, you are in a perfect position to make strides in making the world a safer place for computation. Because really the only two durable solutions that we got out there is crypto, right? We got crypto, we need mathematics to protect us. And mathematics is not subject to software because mathematics is mathematics, right? So things like homomorphic encryption rise above the vulnerabilities of software because they utilize mathematics. The other tool we have that is super important is hardware security. We can use hardware security to eliminate those side channels, because why? Because the hardware creates half of the side channels. The hardware can control what software can do, etc. So I am totally high on the idea of using the combination of crypto and hardware security as a mechanism to really raise our game in terms of how much we can protect systems. So can hardware security defenses enable more durable system security? Absolutely. If you study the program, the DARPA program SIF, where there were 9 teams developing hardware security mechanisms, it's obvious that there's a lot of power in those mechanisms. They're underneath software, they're controlling side channels, they're building mechanisms that you can't step around for certain kinds of vulnerabilities. Really powerful stuff. And today I want to tell you about Morpheus, which was our work inside the DARPA SIF program. And Morpheus is just a system that just tries to ramp up uncertainty in the system to make it really, really hard to hack. And that's really the goal of Morpheus. It's hard to hack. So let's talk defensive strategies, right? You have to build a system that you don't want to be hacked, okay? Now, Can you fix all the software and hardware vulnerabilities? I would argue, no way, no way. If you're building systems that are performant in their end goal, then security is always going to kind of take a back door to that. That can be a great challenge in building a system that's free of vulnerabilities. And the size and complexity of systems today makes it just really unrealistic to think that you're going to get all those vulnerabilities. You can think, I got more than anybody else, but again, we see, every year at pwn, it's not a question of whether or not a system will be taken. It's who will get their exploit off the quickest, because there's so many people trying to break these systems through the many, many vulnerabilities that exist in the system. So no, we're not going to, if you're focused on vulnerabilities, you're in the game, but you're not going to win the game. Definitely not, in my opinion. So can we outwit the attackers? Can we build a system that's just too hard to hack? And that's really, I think, the approach that you want to take. And just sort of put a finer point on this, you don't want to be smarter than the attacker. I think that is impossible, right? If you study the attack community and study attacks, I mean, how often have you read a paper about a most recent attack and you go, wow, that is just amazing. That is so clever. Why is that? It's because attackers are good at what they do, right? So if you're going to try and be smarter than the attackers, probably going to fail. At least I know I would fail for sure. So what we want to do is, in a sense, we want to make them dumber. And the way we're going to make them dumber is to take away information from the attackers. So we're just going to deny them information they need to kick off a successful attack. And then the system will become hard to hack across a wide range of vulnerabilities. Why many different vulnerabilities? Because you're not caring about vulnerabilities. You're just making the system hard to hack. So how do you do that? How do you make a system hard to hack? Well, you've got to build hardware defenses, and you've got to build them in a way that sort of ramps up the amount of uncertainty in the system, so that when someone goes to hack that system, there's too many question marks on the information they need to pull off a successful exploit. And you need to make sure that the things you're using to build those defenses don't use weak security, right? So you don't want to use any software. Don't want any software that you trust. Of course, we got to have software, right? Software is like that. It's like that friend you've got that you love to have in your life and you enjoy being around them so much, but you would never give that friend your wallet, right? So we have a relationship, but we're not going to share anything valuable with software. Software cannot be the source of our protections. Anything that's leaky from a side channel standpoint cannot be, like multi-level cache memory systems cannot be the source of our security. Otherwise, we lose because there's just too many ways to break those systems. So let's turn to what are durable defenses. Now, by durable defense, I mean something that lasts months and months and months, and you know when it's going to fall. You get months of a warning to years of warning when it's going to fall. Cryptography, strong cryptography, right? We knew years in advance that RSA 1024 was not going to be enough. We had to move to RSA 2048 bits, right? That's durable. And then also we need side channel resistant hardware design. So we need to deploy those cryptographic defenses in a mechanism that you can't side channel the information out really easily. If you could do that, you can start to build some pretty durable defenses. And so I want to talk about an early technology demo that we did with DARPA SITH, which was the Morpheus Secure CPU. It was a RISC-V CPU that was deployed into a program called FAT at DARPA, which was a red teaming exercise where a bunch of people tried to hack on these systems. Our system was running a mock medical database, and there were 535 attackers, cybersecurity researchers that worked with our target for 3 months, and we had zero penetration, zero. So there's something here. There's something here. And our level of engagement was very good. People and DARPA kept throwing more and more cash on the pile. So, people really were trying to hack this system. I got a short video for you to show you how it works. This is a little introductory video, something that my students made for our ASPOS paper. And then we're going to come back and look at the details of the microarchitecture.
In a world where software vulnerabilities are rampant and unsafe languages like C are exceedingly common, attackers are gaining more power by the second. To synthesize an exploit, attackers need access to an asset, such as pointer values. Defenses randomize these values to make it harder for attackers. However, hackers have found help around these measures. But there's hope. Because there's Morpheus. To stop attackers from de-randomizing assets, Morpheus changes it from under them in a process called churn. Morpheus is a secure architecture targeted at stopping advanced control flow attacks, such as ROP. We leverage hardware in RISC-V to provide two layers of defenses, displacing memory into a superimposed address space, and encrypting code and pointers. These defenses, combined with churn, significantly hinder exploits. With hardware support, Morpheus can churn sensitive assets every 50 milliseconds with less than 1% slowdowns. With information changing so quickly, attackers are left with a system that is extremely difficult to penetrate and must resort to advanced probing. Because of churn, this challenge becomes a race against a short clock, a race that is nearly impossible to win.
So let's take a look just more generally how that particular approach works. And I'll show you on this slide. And I'm going to use this very qualitative equation. This equation, I mean, it doesn't really make sense, but it makes sense from the standpoint, how do you pull off an exploit? Now, there's a difference between a vulnerability and an exploit, right? A vulnerability is there's a bug somewhere that would allow semantics to be executed in the program that could be potentially dangerous. Now, what's potentially dangerous? Well, you use that vulnerability to extract a key. Use that vulnerability to run your own code. That's an exploit. So vulnerabilities in themselves are not bad. It's the exploits that are bad, and the vulnerabilities lead to exploits. But there's also another part of the system that you have to really get your hands around in order to get to an exploit, and that's the implementation assets. And while the whole world is focused on vulnerabilities, Morpheus is really focused on implementation assets. So what are implementation assets? Those are things like the code, the pointers in the system, the address space and its organization, both absolute and relative distance between memory objects, integers, floating point values, microarchitectural mappings. These are all sort of the underlying representational and state values, microarchitectural state values of the system. And what you'll find is that attackers need to understand these materials to successfully pull off an exploit. Like, there's a whole branch of security analysis called weird machines that specifically try to codify this idea of looking at these implementation assets. So what Morpheus does is very simply, it encrypts them. It just says, okay, here's your code before. Now, the code in the machine used to be defined as what the RISC-V manual says, but now it's defined as what the RISC-V manual says, encrypted by a strong crypto cipher. Same for pointers. Now, once you engage encryption defenses in the system, then the natural response of the attackers is to do side channel analysis on that crypto. They can do it at the crypto level, doing chosen plain text attacks. They can do it at the program level with control and memory based analysis. At the architecture, they can do other memory system type stuff and timing attacks, and they can even go down in the power level to pull information out of your design. So what we employ in Morpheus is encryption with a high amount of entropy in that encryption. And specifically, what we encrypt is code pointers, the code itself, and the address space layout of code. So the layout of code is a cryptographic secret as well. And then the way we get rid of side channels, or we provide side channel resistance in Morpheus, is an idea called churn, where we rekey all of these defenses. So the code is under one key, the pointers are on another key, the memory layout is under another key, and then the other processes have their own keys, and we are rekeying within one of these security domains on a regular basis. Now, what that means is that with 192 bits of true random entropy defining the keys for this crypto that is itself changing again, when an attacker comes to attack the system, they're seeing a version of the system that is unique in time and space. It will never be seen anywhere else ever again. It's completely unique. And so they need to figure out how that system works before the churn cycle and then kick off their exploit. What we're doing at Data Labs, my startup, is we are extending this technology in two ways. First, we're encrypting a lot more items in the system, not just code pointers and address spaces, but also integers, floating point values, microarchitectural state, etc. And we're really upping the number of side channel defenses because we really want to make this system as impenetrable as possible, and additional entropy as well. So let's look at this Morpheus encryption and churn technology. Let's look how it would affect a particular attack. Okay, so it's going to use encryption to encrypt assets, implementation assets in the program. And specifically, it focuses on implementation assets that you don't need to know to program, right? Like you don't need to know what the representation of a pointer is to program. You don't need to know what the instructions of the machine is to program, right? These are typically what we'll call, implementation or undefined assets with respect to the languages that are programming this system. And I'll show you why that is important in a little bit. And then we're going to churn those assets. So we're going to rekey them on a regular basis. And look what happens. This is a buffer overflow attack here. This is kind of attack you're going to see in day one of your security class. And we've got this main function. It's going to call this vulnerable function here. And there's a array buffer overflow in this string copy right here that overflows and then allows you to overwrite the return address of vulnerable. And this attacker here is going to try to overwrite that return address with this string, which really has a pointer value embedded in it. Now on Morpheus, we're just going to ignore that vulnerability. We don't care about the vulnerability. So because we don't try to stop or fix vulnerabilities. We're not crazy. Instead, what we're going to do is we're going to make sure that the representation of pointers is changing with high frequency. So then the attacker goes, well, what should my string look like? I need to understand what the key for pointers is. Otherwise, I'm just throwing a random value into the PC and the system will surely break. So, that's a pretty good defense. Now I can't forge pointers anymore. And then by encrypting pointers, you've essentially encrypted the address space. So where is the return address? How do I get to the return address? I mean, that is a cryptographically hard secret. Even if you leak out a pointer, adding 16 to it is a cryptographically hard problem. So this throws a huge wrench into any attack that uses pointers and code. That's like 95% of them. So it's really broad set of defenses you get out of doing this kind of stuff. And so by churning this, you get rid of the side channels that will allow attackers to infer the values that they want. And you break malicious security attacks. But since you only encrypted undefined semantics, code representation, pointer representation, you don't break normal programs because they don't rely on that information. So this is all happening under a normal program, no changes to the program at all. We ported an operating system, a database, a REST parser to our test system. We never changed the line of code in anything. All we had to change was a few lines of code in the firmware for the system. Really tolerant. The normal software is really tolerant of these changes. So let's see how you can break an emergent attack. Now, emergent attack this is an attack you've never even seen before, but it does use pointers and code in some ways. So in a traditional system that's not protected by any encryption or churn, you're going to find that when you attack that system, there may be a little bit of probing that needs to be done. Maybe there's some ASLR, de-randomization. There's could be a little bit of probing that occurs. And once that's done, you're going to synthesize your attack. Create the code you want to inject, or figure out what value to put on the stack, etc. You're going to implement the attack, and boom, you're in. Now, when you randomize critical assets, so you randomize code, you randomize pointers, then what happens is you don't ultimately protect the system. And this is really when people say, oh, we've tried this code encryption before, it doesn't work. Right, of course it doesn't work, because people are side channeling the information out. it takes hours to get that information out. It's the combination of encryption and the side channel protections you get with churn that make it more durable. If you've ever had a chance to study blind attack techniques like Berkeley's BROP, for example, you'll notice that they don't need to know what instruction set you're on, how you organize your address space. They're just figuring out how to inject code and how to eventually get to the tables they need to get to the functions they want to run. It's really impressive what you can do without a lot of information because of all the side channeling. So just randomizing assets with encryption isn't going to buy you security. It just buys you a little bit of time. Maybe you could detect during this time, but that sounds very difficult. But when you churn, then what you do is you create a time limit over which someone's got to get that information out, and they have to synthesize their attack. Otherwise, you're just spinning your wheels. Things are changing before you get a chance to do that. So that's really a powerful side channel prevention technique that lets randomization really reach its true benefits, randomization and encryption. So let's look at the microarchitecture. We added this technology to the RISC-V rocket core. And I got to say right straight up that RISC-V and the RISC-V ecosystem is truly an amazing catalyst for hardware security. Because when you build a system and you want someone to hack that system, you can't do it with a simulator, right? Because there's lots of stuff that isn't represented that the attackers want. They want those implementation assets. And if you're not running, if your DRAM rows aren't row hammerable because of your simulator, that's like, it's a non-starter. So you really want hardware that is representational of true hardware. And that's something RISC-V is really enabled, really. And plus all the modern software on it is really, it's really amazing. I think hardware security and RISC-V, it's a match made in heaven, something that's really gonna, be a true catalyst for better security in the world. So let's take a look at the Morpheus code and pointer defenses. So code is always encrypted in Morpheus. Now, it's not always encrypted like, SGX is always encrypted. It's always encrypted. Like in SGX, code comes up and they decrypt it in the L1 cache, and then, it sits in the L1 cache open and people can side channel and you get, okay, that's a problem. So, we actually took the step to just encrypt right up to the pipeline. So you're pulling in cipher bits going into the front end of the pipeline. And then we physically isolate the keys and the cipher engines that decrypt that code. So they're not really side channelable because they're just hardware and there's no access to software. And then we do the same thing for pointers. Pointers are always encrypted, not always encrypted pointers like point guard and canaries and stuff like that. Not XOR encrypted and you can look and guess the bits. No, we're talking strong cipher in the registers, in the L1 cache, in the memory system, everywhere encrypted. You're denying software the ability to see pointer values. I mean, that's super powerful. You're not getting rid of the side channels, right? Because you're still going to use those pointers to access memory. And that's going to tell you things about how you get in, where you're accessing memory. So what we do with pointers is we always encrypt them. So we add instructions to RISC-V extensions using the ROCC interface that allow you to take an encrypted pointer and add a non-encrypted constant to it, P++. And you can do relationals on pointers, but that relational is decrypted. So there's some leakage there. Now you can side channel and you can learn a lot of stuff about pointers through this. But you need to do this in order for programs to run, right? Because they, when they take a pointer and stride through an array, they want to know when they get to the end of the array. And then you got to be able to dereference pointers, and you're going to decrypt them at that point. So interesting point here. Even though the pointers in the code are encrypted, there's no change to how we use code or pointers. In fact, when the pointers go to the memory system, they're as you would expect in the unprotected program. But to the remote attacker, to the attacker in the other address space, they're encrypted, and they need to express the pointers in the program's language, which is 2's complement binary encrypted by a strong cipher. And that's a huge bar to get over. You're going to want to start side channeling right away because the key's going to change in 50 milliseconds. Another thing we did, and this was a huge benefit to us and really allowed this project to exist. One of the things you'll find in a lot of hardware security efforts is everyone wants to tag stuff, right? Is this a protected pointer or an unprotected pointer? Is this protected code or unprotected pointer? And when you tag stuff, you have to add metadata to data. And when you add metadata to data, you basically buy in to changing your microarchitecture, your L1 cache, your register files, your memory system. It's a huge effort. And so we made the decision to just say our pointers are encrypted. You want a pointer? It's encrypted. That is our representation. As a result, there's no tagging in the system. There's no memory overhead on pointers. You get a 32-bit pointer or a 64-bit pointer. The encrypted version is 32 or 64. So that really allowed us to sort of just wipe the slate clean of like 90% of the complexity that we would have had otherwise. I mean, I will tell you right now, we are 360 lines of system Verilog on RISC-V core. That's all we are, including the cipher. We have our own cipher. And it's not a problem for normal software. Does normal software care that the pointers are 2's complement encrypted by a strong cipher? They don't care. They just care if I add 1 to it, I get to the next thing in the array. So that's all they care about. And that happens with these encrypted instructions. Now, those pointer tests are real leaky, so you got to have churn to try and protect that. Again, if you didn't have churn, the system would fall in hours. It would fall in hours easily. All right, and so let's look at the microarchitecture. The RISC-V Rocket Core, pretty straightforward, 6-stage pipeline. And what we do is we add ciphers both to the front end to decrypt, cipher engines to decrypt the encrypted instructions. And we also, since we're only encrypting code pointers, we only on indirect jumps and calls and returns. So we have to encrypt on a call, the link register. We have to decrypt the target address on a return, and then on an indirect jump. So it's basically the whole activities in the JSLR instruction of RISC-V. We have to decrypt as well. And so the cipher we use is Simon. And I just want to say, if there's any cryptographers out there, there's a lot of interesting work that can be done in strong hardware-friendly ciphers. We started looking at like AES, and AES is going to cost you 40 cycles encrypt, 40 cycles decrypt in this pipeline. Simon is going to cost you 12 cycles. Karma is going to cost you about 10 cycles. So what we ran was a 12 round, about a 1/3 strength Simon cipher in 1 cycle. So we just added 1 cycle to the front end, 1 cycle to this thing. So and a third the number of rounds of Simon is a lot less strength than full strength Simon, but also note that you only get a couple 100 milliseconds to break that key. So if it takes, instead of 10 years to find the key, it takes 1 year. Your deadline is 50 milliseconds. So and then again, we physically isolated these ciphers, so you really can't side channel stuff out. They're randomly generated keys. Those keys are not accessible by software. And again, no impact on the memory system. The memory system has all encrypted code and all encrypted pointers, but the location of where stuff is in the physical memory, what is contained in a cache line, what is contained in a DRAM row, is exactly the same. No change at all. It's just as it's encrypted. So we don't affect locality or anything like that. It's just a really light touch approach we've got here. Okay, and so 2 places where we have decrypted values. When we decrypt an instruction, there's 1 stage when we're actually evaluating those bits, and then those bits disappear, like in a normal pipeline. And then when we do an indirect jump, the bits get decrypted before they get put into the program counter. So pretty straightforward stuff. We built a couple versions of this system. In summer of 2020, we were getting towards the end of the DARPA program, and DARPA created this FET program, this bounty hunter FET program, where they worked with a company called Synac, who has this like crowdsourced cybersecurity researcher team that they utilize. And so you can put systems up on the web, work with Synac, and they'll get their researchers to come and abuse those systems and find your vulnerabilities. Pretty cool technique they've got. And so we were deployed in the Amazon AWS F1 FPGAs. So a company called Galois built this front end. It was based on FireSim, which is a real nice extension that allows you to run RISC-V in the F1 FPGAs. And so our design was running a server in the F1 FPGA, and running our software, and then the attackers, the researchers would be able to get on that Xeon node and then basically get network access, even potentially log in to the system from the Xeon. And then they work for bug bounties, and they start small and they keep getting higher. I read somewhere, they don't tell, as a researcher, they don't tell us anything, but I read somewhere that the bounties got up to 50K on this particular effort. And so we were running a mock medical database so that we had a REST interface where you could make queries to the database. And their goal was to get inside and pull out this, there was a bunch of medical data that wasn't even accessible from the interface, we thought. And they were supposed to get in and get all this data out of there. As a researcher, all you could see is what vulnerabilities were declared against your system. And you could see the engagement level of your system. And you could see the engagement level with respect to all the other systems as well. And it was just a bar that said, how many hours were people running your systems and trying to basically penetrate your systems. And I could always see when, whoever was running this program was throwing more piles of cash on there, because you'd see the slope of engagement would go up and up and up. And towards the end of our run, they did this high value payout. What that means, I don't know, but it was a SQLite to RCE attack, so remote code execution on SQLite attack. And this was a known vulnerability in our version of SQL. So it's not like they had to find a vulnerability in the code. It was there. They just had to successfully launch an exploit based on that known vulnerability. And I could see when that high value payout came out, we were sloping way higher. In the end of the program, we were the second most engaged target in the FET program, but had it gone maybe 1 or 2 weeks more, we would for sure been the most engaged program target in the FET program. And I'll just say we had zero penetrations. People were trying to hack in, they didn't get it. Now, is Morpheus unhackable? There's a lot of press out there about this result, and people always say, oh, it's an unhackable chip, it's an unhackable chip. Is Morpheus unhackable? I would say no, it's not unhackable. Therefore, it is hackable. It is incredibly hard to hack, though, and I think you'd have to be monumentally patient to hack into Morpheus. I think you really have to be patient. Anyway, let's talk a little bit about the evolution of Morpheus and beyond, and that relates to the hackability of Morpheus as well. And really, the evolution of Morpheus is for me, it's becoming more and more interested in privacy. This idea that we can have information on a system that people cannot see, like these pointers in Morpheus. That is incredibly interesting. And it's inspired by technologies like homomorphic encryption, which do the same thing, but are very, 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 very expensive. So we are commercializing a derivative of Morpheus, encrypted pointers, as well as additional technologies in my startup, Edita Labs, which is a spin out of the University of Michigan. So let's talk a little bit about this journey we're on. This is the tail end of it, and then we'll close up this talk. So again, is Morpheus hard to hack? Yeah, it's way hard to hack. Is it unhackable? I would guess no. It is not unhackable. It could be hacked. I don't think you could do it without automating the attacks, and B, you'd have to go stochastic. You'd have to use some sort of stochastic method, just because there's just too much uncertainty in the system. You're going to be guessing. And so I think you'd need to have a lot of time. And then if you had to stack vulnerabilities, if it was a blended vulnerability, it could be very, very difficult to penetrate the system. I think it'd be really hard, really hard. Anyway, I know this because I had this guy, Shibo Chen, and Shibo has a reputation at University of Michigan. He's my PhD student, but he was an undergrad when he worked on this thing. He's got a reputation as being, one of the sharpest tacks in the toolbox. And he was telling me, yeah, this is hard to hack because you can't forge pointers. You can't do relative address attacks because you have to do the arithmetic remotely on a pointer you've leaked out. And once you do that, you now have this, it's a cryptographic secret what the address space orientation is. So that is really tough. And then the churn really places this limit on the amount of time you have to solve these problems. So that's why you really got to go stochastic. You got to just ignore the churn, assume that the address space is completely random, and just stab your way in and see what happens. So you're going to need fast restart ability. It's going to be tough to hack this in, but certainly, in my opinion, is possible. But what it does in the end, in the final analysis, is it denies information to attackers. And when you deny information to attackers, you've built yourself a pretty durable defense, right? I think if we put Morpheus out there, if we commercialize it and push it everywhere, I think it would take a long time for people to develop techniques to penetrate it. And I think what we'd see is that we would see over time the amount of time it took to penetrate it would slowly decrease as people figured out ways to sort of ease some side channeling into that. Which really led to the question that led to the startup was, what else can we deny attackers that would be interesting? And I think there's a lot you could do. But again, we want to use the same mechanisms as before. We don't want to use software. That's a non-durable defense. We don't want to have side channels and use leaky operations. We don't want to share resources with the main core. We want durable defenses, and we want to deny all kinds of information to attackers and build on top of that base. And so again, we want to lean heavily into strong cryptographic defenses, and we want to build side channel resistant hardware design to stop information leakage. Because once you put that crypto up there, they're going to try and stop, you're going to try and break your crypto and leak out information. And then it's just, from a standpoint of security, it's really a lot more than just stopping someone from hacking into a program, right? I mean, that kind of is the focus of everything in, the IEEE SMPs and the computer architecture security tracks. Everything is hacking. But let's talk like security. What does it mean to make something secure? Well, it means you have to solve the CIA cubed problem, as we call it at Agita Labs, which is confidentiality. Can you ensure that no one will see this important secret that I have inside my program? Well, today we do that is we say, if you can't hack into the program, you can't see my secret. It's a pretty weak defense. Integrity. Is it possible for someone to break my computation in a way that benefits them? Like, does the ATM add my deposit to your account? That I don't need to know anything about your deposit. I know it's positive. And so that's an integrity check. Authenticity. I want you to compute on my data. Did you actually use my data, or are you just fooling me with your own data? That's a very important aspect. Access control. Should I even be able to access this data? Should this machine be able to access this data? Should I be able to access it now and next month? And then availability. How do you prevent someone from denying access to the system? What are the mechanisms to try and prevent that? If you can solve these problems, then you can take the whole CVE, the whole CWE database, and just push it to the side. Because those things will have no agency over this thing that I've built. And I'll tell you, that thing that I've built will be made of crypto and hardware security. It won't have software in it, because if it's got software in it, then it's not very durable. And if I do that, then I can expect months to years before my defenses fall. And that, I think, is a really tantalizing aspect of pushing heavier and heavier into hardware security. This idea of months to years before we know something will break. You won't have to get up the next morning and say, oh my gosh, there's a bug, cancel the wedding. It's really the case that you're going to have lots and lots of warning that your system will fall. So here's what we're building at Agita Labs. We're building this thing called the ØZone, O spelled with a 0, Secret Processing Unit. And what it does is it just processes secrets, right? It allows you to take third-party data. What is third-party data? Third-party data is data from somebody else who doesn't trust me. In this scenario, me, the programmer, is the attacker, right? This is SolarWinds proof security if it works, right? Because now we don't trust the programmer. But I want to provide a service to this particular person. So she's going to encrypt her data. She's going to attach a contract to that data. And that contract is basically DRM. It says who can use this data for how long and what can they do with it, right? That is and this changes it from security to privacy, because security is about stopping hacking and protecting programs. Privacy is about having control over your information, which requires security, of course, but it requires way more than just security. And then we're going to push this data into the cloud. So I'm a cloud provider, and we target Azure and AWS cloud, FPGA nodes in the cloud, and we have our secret processing unit, and our customers, which we do not trust. I'm sorry customers, we do not trust you. But that is the value of our proposition, is that we do not trust our customers. Our customers can write software to compute on that third-party data, and they themselves cannot see that data. Now, that third party can also be our customer, and they can secure the database, and only the chief security officer has the keys and the ability to see that data. So you can use it both for just general database security, or you can use it to provide a service in a way that allows you as an ØZone user to take someone else's encrypted data, compute on that encrypted data, get results that are computed in encrypted form, but you cannot see that data. You cannot side channel that data out of the ØZone SPU. All you can do is take the encrypted results, send them back to the third party, and they can decrypt them and see that data. But because of this hardware technology that we built, we can do much more interesting, exciting things. If granted by the third-party data owner, information can be released in unencrypted form. And so now it's possible to release privacy-preserving statistics, like a voting machine could say, hey, we don't know what your vote is, but we know you didn't vote for any of our candidates. That's a privacy-preserving and important aspect of a voting machine that requires a decrypted Boolean value. Or you could even lean into something like differentially private statistics and release statistical information and generate knowledge from encrypted data without seeing the underlying data. So super exciting. And the way you do this is you lean into cryptography, you lean into hardware security that's side channel resistant. And you end up with a system where you don't trust that main core. That x86 core that we couple with, we don't trust it. We don't trust the hardware. We don't trust the software. Nothing. In fact, everything is checked on the SPU side. Did it send me the right instructions? And then all the core sees is encrypted, protected encrypted values. And what's also interesting is we don't trust the programmers. We don't trust programmers at all. Programmers are untrusted. They don't get to see the data. They get to write the programs. They don't get to see the data. They can see the data when it's allowed by the third-party data owner. Change the program, you're not going to be able to see that data. So really, really cool technology. And then because we're doing hardware security here, right? This is a processing unit for secrets. We can build it in a way where software side channels, crypto side channels, memory side channels, architectural side channels, timing side channels, and power side channels have no agency over the system. We can really lean into all the great technologies being developed in the hardware security community and really protect it. And then the applications are really wild. Like you can secure a database. You can have a database where you could have information in your database that you yourself can't see. Only your customers can see it. You know, end-to-end encryption support, no problem. Or you can encrypt your database, work on it, operate on it, and never ever have anything decrypted. Someone hacks into your system, what happens? They can steal your ciphertext. That's not too useful. It's great for private machine learning, federated learning, home and health monitoring. I mean, we're you know, I've got this this Fitbit. You know, there's the Apple Health monitoring capability, sending megabytes of data up to Apple every. You know, it's great stuff, and they want to look for stuff in that data, right? They want to see, do I have an arrhythmia? You know, or home monitoring. Are there any faces in my house when I'm gone? I mean, that requires those service providers to have access to what's happening inside our house. Could we do that without them seeing it? That's really exciting technology. Genomics analysis, something that's getting clamped down hard by legislation. Can we continue to build medicines and medical treatments off of genomic information if, you know, regulations are getting really strict about that, and security, et cetera, all kinds of stuff. So we're super excited. If you want to learn more about this, we have software evaluation kits available. We're looking for proof of concept applications. We'd love to work with anybody that has a very interesting application that needs really high security and would add value to their endeavors by being able to process information that they themselves cannot see. So please give me a holler. Thank you so much for listening to my talk, and I'd be glad to take any questions. Thank you very much.
Thank you, Todd, for this enlightening talk. We have actually quite a few questions.
Awesome.
So Leslie,
first question comes from Paul, and he says, can this be implemented?
Leslie, can you get closer to the microphone maybe a little bit?
Sure. Is this better?
Yes.
Great, thank you. So our first question, Dr. Austin, comes from Paul, and he asks, can this be implemented on Boom?
Yeah, for sure. So just a little background. Boom, I believe, is the out of order version of the popular RISC-V open source core out of Berkeley. Yeah, no problem. In fact, all of our technology is sort of buried into the functional unit. The functional unit that implements JALR, J-A-L-R, it's buried. It's just crypto's buried right in there. And then we just add one stage to the front end of the pipeline. And I know Boom has shares most of the front end with Rocket Core. So I think it would be a pretty easy port from what we did to Boom. Yeah, I think it would be pretty easy. There's no, the fact that you're doing out order and that stuff, it's not a big deal because that's just, how you're dealing with dependencies and such. And there's nothing secret about the dependencies. What's secret is the addresses themselves.
Great, thank you so much. And another attendee asks, any thought on how should we evaluate how secure a system is? Any metric? Does any metric exist or new ones are needed?
Yeah, that's a great question. So I always say to my students, they'll probably have heard this 1,000 times, that strong security claims plus $4 will get you a venti latte at Starbucks, right? They're completely worthless. And so in my mind, the strongest metric of security is how long has this system not been hacked? Now, beyond that, we can do a lot of things, right? Like Simha Sethamadavan at Columbia University. He's been doing a lot of work on side channel analysis of systems. He calls it side channel vulnerability factor. This idea that you can take a system, operate that system, and basically use machine learning and similarity analysis to see, are there any correlations between the secrets in the system, which are revealed to the analysis, and the measurable aspects of the system. Very interesting. And then Jakub's talk last week also had similar aspects of that. So I think there's metrics of security for software, but I kind of want to abandon those. So if you're focusing on systems that have strong crypto and rely on hardware security for side channel resistance, we have the metrics. The metrics in strong crypto are basically how long has this been since it's been busted, the cryptanalysis, and in the hardware security domain, we're seeing those side channel vulnerability metrics emerge. So that's what I would really focus on myself.
Thanks again. And our third question is, how are you verifying core operation? Formal methods?
Good question. So great question. We did no formal methods. So we were a shoestring budget, 3 grad students and 1 overworked. Well, I guess the grad students were more overworked than me, but I felt pretty overworked. So we didn't use any formal methods. We just basically wrote, there's a company called Galois who generated a bunch of test cases for a variety of attack classes. So we could show that we could stop those. And then we ran a bunch of benchmarks. Like we ran my bench just to test function. In terms of verifying security, not too much. But I will say in the startup, we're verifying privacy. So that's a really interesting thing to look at. I've been talking, I see Jason Oberg on the line here. Jason and I have been talking a lot. Jason's at Tortuga Logic, which does a lot of hardware analysis work for security vulnerabilities. I've been talking to Jason about how do we sort of rework some of that technology for privacy verification. Like, is there enough entropy in all of my ciphertext? And is there any timing analysis that can leak information out of the system? I think all of these things, we can put strong mathematical proofs behind all of these things. I believe, especially since we're only worried about ciphertext strength and we're only worried about side channel analysis. I think it's certainly possible. Great question.
Thank you. Our next question says, you have mentioned that it is very hard to hack in terms of various types of attacks. is the design resilient against fault injection attack, for example, optical fault injection, clock glitching, or voltage glitching fault injection, or so on? If yes, how would you evaluate the susceptibility/resilience? Is there any research work going on out there?
Yeah, awesome question. I would say Morpheus, no. ØZone, yeah, for sure. And here's the reason why. So if you haven't read up on fault attacks, they're so interesting. The basic idea is you're going to inject faults into some sort of critical operation, and that's going to reveal, sort of unfaulting that computation is going to reveal something about the system that you want to know. Okay, so in Morpheus, I mean, you know, if you're sort of fault injection attacking crypto cores, right? That is you're manipulating a multiply, for example, is typical of what I've seen in the past, to get a broken digest or signature to come out of a system. Morpheus have no agency on that particular thing. Now, can you do that to the ciphers that are inside of the Morpheus pipeline? I don't know how effective that would be, because you wouldn't have any observability on what your injection did. So I don't think it would help you too much there. But it's just in terms of, you know, like breaking a crypto algorithm, it wouldn't stop that. And that's you know, the problem is it's not really system security. That's really cipher implementation security. And then so then you go over to the ØZone side of things, and you know, ØZone's a coprocessor. So with ØZone, we can build, you know, all of the, you know, we can do all the canary circuits, all the kind of things you need to do to make sure that kind of stuff can't happen. So you basically just shut down the system if somebody starts manipulating your voltage. So because it's not sort of directly stuck in the x86 core, and it, you know, shares a huge power and clock line, I think it's much more protectable. And so I really like this idea of physical isolation of your secure component. I love the idea of taking what's secure and moving it over to something where the decisions you make when you design this is, I don't want to be faulted. You know, I mean, I don't think you would ever build a high performing about, because slow it down and add a bunch of stuff to it in a way that you know, essentially made it not as good as it was before. So I love the idea of divide and conquer here, you know, let the fault attacks happen on the main core, and then move all the really sort of important secure stuff over to your secure core. And there's lots of defenses for that. Thank you. Great question.
Our next question is, I'm sorry.
Leslie, I think we're coming to the hour in here. But as expected, you know, Dr. Austin's talk is drawing a lot of questions. I mean, the screen just keeps rolling with questions.
Correct.
But I think for these questions, I would highly advise the people who are asking them to contact Dr. Austin privately, and basically seek some answers to them. I'm sure he's going to be very happy to respond to a lot of this, because they are quite intriguing, actually.
It's actually faster for me to just do them now if you want to continue a few minutes. Or we can stop this, and then I'll just roll through the rest of it. You do not want to go into my email box, people.
Oh.
we just don't share the recordings with our audience. Yeah. But if you're available, and if the person who asked the question is available to stay later, would that be okay?
Yeah, sure.
The directors.
So how does a key? Yeah, just 2 minutes. I can do these 2 minutes. 3 minutes.
Okay. How does the key?
So how does the key get?
Into the hardware?
There's an RNG. It's just an RNG value. So there's an RNG core inside the pipeline, and you just tap off it. So you know and that RNG is dependent on temperature and bus transactions. I mean, we're basically taking any piece of entropy we can get our hands on and shoving it into the RNG. So that value is, in my opinion, is unguessable. And then we didn't do context switches, you know, so we didn't really have to worry about, you know, there was only one security domain. If you want to do context switches, you have to get that key out and save it. So then what you could do is you could have a master RNG key that would encrypt the key that was saved to the operating system, and then you could restore it again. So that would work. And then Morpheus relies on centralized temporal randomization. How can we now resist the attacks against this
Centralized control block that handles the randomization? Who handles the security control policy?
Well, that is a TRNG key feeding into a encryption cipher. So the randomization is implemented just with crypto. So crypto is a useful randomization technique because if you grab a random key, you get a one-to-one nonlinear mapping between the input domain and the output domain. So the policy is grab a random key and have a completely random output. When you do churn, you need to ensure that you can be under two keys long enough to sort of get everybody under the other key. And so the way churn works is you got to basically push all of memory through a unit at some point so that it can see, is it under the old key or the new key? And if it's under the old key, move it to the new key. And then so there's a little bit of operating system to help do that. But the only thing we have to trust the operating system can do is it can complete that operation. We don't rely on it for actually encrypting and decrypting. And then which protocols are used for the key provisioning? What kind of attestation is used to guarantee a remote user in case of a cloud implementation? What kind of form of methods? So, and with respect to Morpheus, the protocol is very simple. It's just a randomly generated key. So that is secret to everybody. No one needs to know that information. Just the memory system, the microarchitecture needs to know it. So there is no provisioning other than every churn cycle, you grab a new random key and use that to decrypt the pointers. And during churn cycles, you got to have two keys because you don't know which one of them is in use. And then I would say in ØZone, you're going to use all that is going to be just standard PKI, certificate of the chain of trust and all that. I don't want to get into those details, but fortunately, cryptographers have invented all that technology for us. So we just have to use best known methods to solve those problems. And what are the performance implications of churn? Other than an additional pipeline step, does the CPU have to re-encrypt everything once the key's churned? Yeah, churn is awesome because it's this knob, right? If you turn it up really high, it'll consume half of the cycles of your system, right? You'll run basically half as fast. But if you turn it down low, you can consume however many cycles you want because it just kind of picks up again after so often. And so what happens is you basically have to make a judgment, like how fast do I think somebody can side channel this machine? And the approach that I really like is use attack detectors, right? We've seen a lot of work in the community on attack detectors. And what attack detectors do formally is they kill the program that the attack detector triggered, which isn't also always a good thing. What if your attack detector just initiated a churn, right? And the churn doesn't break the program. It's expensive from a performance standpoint to do a full churn. But if you're only doing that, like when somebody does arithmetic on a code pointer, you should never do that. Then you can trigger that operation. Otherwise, we generally run it really like on the Fed system. It was on the order of, I would imagine, on the order of minutes between churns. And does Morpheus cause delay in instruction process? So Morpheus causes additional delay on mispredicted branches because there's a longer front end. So we definitely want to kick in that G-share predictor on the Rocket core. So that really mitigates that loss by quite a bit. And then on jump and link registers, on any jallers, call, return, or on a indirect jump, you're going to see an extra cycle of latency. But how often do you do that stuff? And taking an extra cycle there, it's really hard to experience that in a program. Oh, does Morpheus resist against random hammer attack? Is that row hammer? I don't know the random hammer attack. It sounds interesting, but just row hammer definitely protects against row hammer to another address space, right? If you're row hammering yourself, right? If you're row hammering yourself, thanks. If you're row hammering yourself, then you can generate any address you want, and it'll be encrypted properly for you. So you're within the security domain that we're. And that was a hammer yourself kind of thing. But if you're hammering another address space, it's really tough, because now you need to figure out, how do I express a pointer in the other address space that matches the next row above or below. So that's pretty tough. That would be pretty tough. Okay, and then how did you randomize the pointer memory? Is it dynamic, or just randomization happens at the initial level while the program loading the execution? Okay, great question. So for what we did, what we did for FET, we ran one address space physical. We didn't get to virtual memory on that. And then so what we did is we randomized the address space in. We had what's called a boot time key. So there was a shared key between the compiler and the firmware on the system. And so you would be randomized in the flash, and then you would come up, and then what the firmware would do is the firmware would kick off a churn cycle right away, so that that you were only vulnerable to someone discovering your boot time key during the time you were booting. And I'll tell you, people tried to get our boot time key like you would never believe. We got like 4 different cases of people trying to give us your boot time key. It's not fair to hold the boot time key back. We never gave the boot time key out because, why would you give a key out? We shared all the code. We let them build all the programs they wanted to build, but I'm not giving my boot time key out, So anyway, thanks for the question. Thank you all. I think we're at the end.
Yes, thank you so much, Dr. Austin.
Yeah, it was a huge pleasure. It was a huge pleasure.
Yes, and thank you everyone for attending. One last thing, I just shared a link for a poll that we'd love for you guys to complete. It should take only a couple seconds, and it'll give us feedback on future webinars. Thank you, everyone, and thanks again, Dr. Austin. Stay well.
Ciao. Be well, everybody. Hope to see you again soon in person, real soon.
Likewise. I'll stay on the line in case anybody has questions for me.